We have been looking at deterministic finite automatas for a while now. In deterministic finite automata, there are two key words. One is deterministic and another is finite. Okay. So finite means that there will be finite number of states. Finite number of states. Okay. So what you are doing while you are constructing DFAs, mainly what you are doing is you are defining state transitions. You are defining state transitions. That's what you do while you are constructing DFAs. Now in DFA, you have a finite number of states, and these state transitions are going to be deterministic. The state transitions are deterministic, means that from any state and you see any symbol, there is a certain move to another state. So if you represent, let's say, capital Q is the set of a state. Okay, Q is set of a state and this is alphabet. Then being at any state, looking at any symbol, you will go to any other state. That's what state transition is, and this is unique. And because of this determinism, you have a unique computation path always. For a given string, right? So these are the observations that we have made so far. Every string will follow a unique path because of determinism. Unique path because of determinism. And when I say unique path, what you mean by unique path is that the transition of states, the course of transition of states will always be same. Any number of time, if you give DFA to the, if you fed the string, a particular string to a DFA, any number of time, it will trace a unique path on it always. Okay, so it will trace a unique path. You give a string to a DFA, it will always trace a same path, same unique path. Now there is a finite number of states. Number of states is finite. Number of states is finite. And number of states is finite means the state transition will happen within these states only. So if you have a, let's say if this is your DFA, this is the finite control of a DFA, you have states and this is the number of states is finite. So whatever transition will happen, it will happen within these states. Okay, it will happen within these states. And what we do is we give a string W and we record the sequence of states. Okay, and we record a sequence of state. Now if we give a string W, this W will be there in the input tape, and your tape head would be pointing at initially at the first symbol, and with every transition your tape head will move towards the right. Okay, and what will happen is initially you will be at Q0, and then with every transition you go to another state Qi, then you go to another state Qi plus 1, and so on. So for every state there will be a corresponding sequence of states, and this will be a unique, because every string will trace a unique path always. So for a given string the sequence of state is unique. This is what a unique path is. This is what a unique path for a string in DFA. Right? This is unique path because of determinism, because of deterministic transitions, right? Okay. In case of finite languages, we have made an observation. In case of finite language, if W belongs to the language, this sequence of state will have no repetition. This sequence of state will have no repetition. Yes or no? We have seen this thing. So this string, this was a finite language, and we see that sequence of states before you reach dead state. Okay. So what about, let me take a string that is a part, because W1 does not belong in this example. W1 does not belong to the language, but if we take any W2 belonging to the language, example of it, let's say we take AB. So W is AB, and the sequence of state, say S, W2 is sequence of state S2. Initially it is at Q0. On seeing A it goes to Q1, and on seeing B it goes to Q2. Q2 belongs to the final state, therefore W2 belongs to the language of M. So if in case of finite state, if in case of finite language, if the string belongs to the language, the sequence of the states will have no repetition, right? So all the states will be different in finite language, and if W does not belong to the language, then till you reach dead state, sequence of states have no repetition. Sequence of states have no repetition. Once arrive at dead state, dead state will repeat. Right? So this was about the finite language. Similarly, and this is sequence of states have no repetition. Sequence of states have no repetition. When sequence of states will have repetition? So if this is your Qi and this is your Qi plus 1, this is Qi plus 2. If you always have a forward move, or if you have moves in one direction only between the states, definitely the state sequence generated will have different states. In case of finite automata, this is what happens when you construct a DFA for a finite language. If you take an example of any finite language, let's say this is AA, BA. If you take this example, this language is what? If from Q0 you will either be looking to see AA or BA. That's what it is. Similarly, if you have more number of strings, even if you have, let's say, A1, A2, A3, you have n strings. What you are going to do while you are constructing DFA is that you are going to look these n strings. you are going to construct DFAs in a way that you are looking for A1, you are looking for A2, you are looking for A3, or you are looking for AN. That's how you construct the DFA. So giving a DFA for finite language is straightforward. That it is A1 plus A2 plus A3 plus so on plus AN. So you're just looking to accept you're just looking a sequence of states for A1. Okay, you will be looking at sequence of states for A2, looking at sequence of states for A3. Here you know the number of strings to be finite, and then you can go on for each and every string and give a sequence of states to accept that string. So if the number of strings is finite, then you can, for each and every string, you can give a sequence of state to accept that string. So if A1 is AA, you can give a sequence of state for AA to accept it. For if A2 is AB, then you can give a sequence of state AB to accept that, right? Let's say A1 is AA, A2 is AB. There may be some AI, which is let's say AA, AB, B, AA. Okay, so the length in this case is 3 plus 2, 5 plus 2, 7. So it's a 7 length string. To accept this 7 length string, definitely your number of state is going to be 1, 2, 3, 4, 5, 6, 7, 8. So to accept the 7 length string, the number of state is going to be 8. Now this is your finite. This is your finite language. Okay, from A1, A2, so on, AN. Let's say AJ has maximum length. Right? Length of AJ is greater than length of any AI. I is equal to 1 to n. Okay, so length of AJ is greater than any AI. Let's say, then your deterministic finite automata. Will have, if AJ has say length of AJ is k, then your deterministic finite automata will have, this is first to Q1, Q2, then deterministic finite automata will have k plus 1 states. Okay, k plus 1 states. You can construct DFAs in finite number of states for a finite automata. So it is simple to give DFA for finite language. It is simple to give DFA for finite language. So it is possible to give DFAs for all finite languages. So all finite languages are regular. All finite languages are regular.